Okay, let's begin Chapter 3. In Chapter 3, we mainly introduce energy-based models for modeling conditional distributions, such as P of H given X. So the applications are mainly discriminative tasks, such as speech recognition and natural language processing. We'll have three sections. First, let's introduce conditional random fields as conditional energy-based models. Okay, in general, CIF is a conditional distribution P of y given x defined as a directed model. The conditional distribution is defined to be proportional to the exponential of sum of potentials over clicks. X is the observed sequence, which is also given. Y is a hidden sequence, and since X is given, it can be removed from the graph, and we consider the subgraph induced by Y. And for only the clicks in the subgraph, we can define the click potential phi C of YC and X. Again, since X is given, it can be treated as a constant, so it can be included in the definition of the potentials. This is a general introduction to conditional random field. Next, we'll introduce the neighbor bias and the exposure bias suffered by locally normalized models, which are avoided in CIFs. Okay, in locally normalized models, we see that the water probabilities at each time step are locally normalized. So successors of incorrect history receive the same total mass as do the successors of the two history. So this will cause some problem. Intuitively, we would like the model to be able to revise an earlier decision made during search when later evidence becomes available that rules out the earlier decision as incorrect. But since the model is locally normalized, the successor of incorrect histories receive the same mass. So the label bias problem means the locally normalized models often have a very weak ability to revise early decisions. It can be proved that globally normalized models are strictly more expressive than locally normalized models. An exposure bias refers to the mismatch between training and testing of locally normalized sequence models. The training is taken by teacher forcing, that is, maximize the likelihood of each successor target word conditioned on the goal history of the target word, and testing the model predicts the next step using its own predicted samples in testing. So the model is never exposed to its own errors during training, and so the inferred history at test time do not resemble the golden training histories, since the inferred history at test time often contain errors. It can be seen that the exposure bias results from training a certain way, so it may be alleviated by some methods such as scheduled sampling, but label bias suffers from the inherent properties of the model itself, so it is more difficult to overcome the label bias. Okay, here comes linear chain CIFs, which is widely used in many NLP tasks. Many NLP tasks can be cast as sequence tagging tasks, such as speed tagging, shadow parser, Chinese word segmentation, and so on. The dominant approach is to build a linear chain CIF under the label variables y forms a linear chain. Traditionally, the linear chain CIFs are mostly log linear models with discrete features. Over the linear chain, we could define the node potential and the edge potential. Traditionally, people use discrete features, so the resulting model is a log linear model. The features are usually handcrafted, such as we shown here, which people may think what features are useful for tagging, then they can add to the node potential and edge potential. Recently, people develop neural CIFs, that is using neural networks, for example, LSTM to extract features. LSTM is built on the input sequence to extract features which denoted by H1 to HT. The node potential can then be calculated from these hidden states or a linear layer. As shown here, we omit the bias in describing linear layers throughout the tutorial. And phi t k is an abbreviation which denotes the potential value at position t for label k. And the edge potential is mostly usually implemented as a matrix A. Okay, next we'll show you how to train CF in general. The CF is a continuous distribution which is defined to be proportional to the exponential of a potential use theta. And here is a normalized constant. And the objective function is a conditional scaled log conditional likelihood of training data. Take the gradient with respect to theta. We have such a equation. There are two terms. The first term is sum over training data, which we often call as the empirical expectation. And the second term is obtained from taking the grad of the log normalized constant, which is often called as a model expectation. For linear chain CF, this expectation can be exactly calculated, for example, by the forward and backward algorithm. Here are some further details. Okay, we have the model, and the potential is defined as the sum of node potential and edge potential. Node potential is phi t at time t over for label yt, and edge potential is a matrix indexed by yt minus 1 and yt. The network is trained to optimize the log conditional likelihood. Important quantity is a gradient with respect to the potential value at each position. If we can calculate the gradient with respect to phi tk, then the parameters of the network can be derived from this quantity based on the backpropagation procedure. It can be shown that the gradient is equal to the difference between the between the empirical state occupation probability and expected state occupation probability. That is, the difference is error signal received by the neural network extracted during training and then backpropagate through the neural network. The second term, often called the gamma, is often called the posterior state occupation probability, means the probability of being in state k at time t. It can be calculated using the forward-backward algorithm as introduced in Rebecca's tutorial on hidden Markov models. Okay, here a brief summary of conditional random fields. conditional random fields is a conditional distribution defined by random field, and sometimes in order to explicit the role of the length, we could introduce the subscript L to denote sequence length. And CIFs have been successfully applied for various sequence labeling tasks in LP, but less so for ASR. The reason is that in classical definition of CIFs, the input X and output Y are of the same length, but in ASR, the label sequence and the acoustic feature sequence are often in different lengths. So historical people relies on state alignment to align so that CIFs can be used for phone recognition. In the next 2 sections, we'll present how to develop a CIF model for end-to-end ASR, and then we show how to improve CIFs for natural language labeling. Okay, so for ASR, a recent trend in ASR is to develop end-to-end ASR models. Yep, so here are some basics. Basically, ASR is a sequence discriminative problem. That is, for acoustic observation X, find the most likely label sequence Y. There are 2 main issues for developing end-to-end ASR models. First is how to obtain the posterior of labels Y given observations X. To be end-to-end, we need a differentiable sequence level loss of mapping acoustic sequence X to label sequence Y. I'm sorry, this is a typo here. And the second, we need to handle alignment since the 2 sequences usually differ in length. There are 2 approaches, explicitly or implicitly. Explicitly, we can introduce hidden state sequence pi as in connectionless temporal classification, CTC, ion transducer INT, and the CIF we are introduced. And implicit as in attention-based encoder-decoder, the AED. Let's look a short overview of recent end-to-end techniques. There are 2 interesting points. First, CTC actually was proposed before DNHMM was proposed. And the second, INT was proposed before AED. So just let you know these 2 interesting facts. I leave this for your own thoughts. Okay, so how to develop a CIF model for end-to-end speech recognition? We would like to first introduce CTC. CTC is introduced by Graves in year 2006. The motivation is to training the conditional model without need for frame level alignments between the acoustics X and the transcripts Y. The idea is to introduce a state sequence pi 1 to pi t. And further, CTC introduced a blank symbol B. So the possible values pi t can take is a union of the standard labels and the blank symbol. Suppose the alphabet size is k, the number of possible values that the state pi t can take is k plus 1. We usually use use any kind of neural network to calculate high-level features from the raw speech features And for each frame, we obtain HT. Or say we can encode the speech features into the H. Then we can apply linear and soft layer to calculate the posterior of pi t. The unnormalized outputs ZT from the linear layer and before softmax are often called logits. The state sequence is often called a path, so that the path posterior is defined as a product of the state posterior. Next, we need to define the state topology in pi so that we know how to map pi to y. CDC actually defines a special topology. For example, here, these three paths all map to CAT. All possible paths corresponding to a given y can be coded in such a lattice. From top left to bottom right, there is a path. With such a mapping, the posterior of label sequence y can be obtained from the state posterior by summing over all possible paths. Okay, so we introduce the basic idea of CDC. A shortcoming of CDC is its conditional independence assumption. This can be easily seen from the graphic model representation. The state pi t at different times are conditionally independent with each other. There are two ways to overcome this drawback, either using INT or developing CDCCF. Okay, let's move on to introduce CDCCF. We'll introduce the motivation, related work, the method itself, and finally the experiments. And please refer to the papers for details. CDCCF would help us to develop data-efficient end-to-end ASR. A recent trend is to develop end-to-end system, that is, to eliminate the construction of GMM gems and phonetic decision trees, and can be trained from scratch, and in a more ambitious sense, remove the need for pronunciation lexicon, and even further, train the acoustic model and language model jointly rather than separately. But these ambitious end-to-end models tend to be data-hungry, which requires tens of thousands of hours of lab speech to achieve state-of-the-art results. So we'd like to develop data-efficient end-to-end speech recognition, which can flexibly use a separate language model with or without a pronunciation lexicon. This is desirable since text corpus for language modeling are cheaply available, so that we can build a separate model for plug-and-play use. And if we have a lexicon knowledge, why we not use it? So in this way, we can achieve data efficient. The technical idea is to keep necessary factorization of AM and LM, since modularization promotes data efficiency. The history conventional system is a hybrid one, which uses separate AM and LM but has an awkward pipeline. The recent end-to-end system has a simplified pipeline but tend to be data hungry, so we would like to bridge the benefits of the two approaches. Okay, so we can develop CDCCF. Like CTC, we use explicit alignment to define the posterior of y from posterior of pi. CDC assumes state independence for state posterior. In contrast, we use CRF to define the conditional distribution of pi. The key is to define the potential function, which consists of load potential and edge potential. Load potential is defined to be the log posterior of pi calculated by neural network, and the edge potential is calculated by n-gram denominator LM of labels, like in lattice-free MMI. In this way, we can avoid the conditional independence of CTC. CTC-CIF training follows the standard method in training CIF as we introduced before. It takes the gradient of theta. There are a difference involving two terms. The two terms can be calculated using forward and backward algorithms, similar to calculations in lattice-free MMI. Here are some further details. The model is set up. Label posterior is the sum over state posterior, and the state posterior is defined as a random field which consists of load potential and edge potential, and the network can be trained to optimize log conditional likelihood. As we introduced before, in training CF in general, an important quantity is the gradient of the log likelihood with respect to the potential value. Okay, the potential value at time t for label k. If we can calculate such gradient, then the gradient for all the parameters of network can be derived from this quantity based on backpropagation procedure. And it can be derived that this gradient is equal to the difference between two expected state occupation probabilities. The first term is posterior state occupation probabilities by running the forward-backward algorithm over the WFST, or determined by the label sequence. And the second term is the posterior state occupation probability by running the forward-backward algorithm over the WFST, determined by the n-gram language model of labels. These two terms give a difference, which is the error signal received by the neural encoder during training and then backpropagated the network. People may wonder what the edge potential in CTC-CF looks like. Here we show you some more details. The edge potential in CTC-CF is defined as in this formula, the n-gram probability of y determined from pi. If we denote the WFST representation of CTC topology by T, and the n-gram LM of labels by G, then T and G can be composed into a single WFST, and it can be seen that a path in the resulting WFST corresponds to a state sequence pi. The path weight corresponds to the n-gram LM of the state sequence pi. The graphic model representation of CF contains higher order interaction between pi states, but it is a complicated one. We can see it in an equivalent form. The idea is to take the arc in the WST as a state, so that this CF can be seen equivalent to a chain CIF, and the occupation probability needed in training can be calculated from the occupation probabilities of the arc by running forward and backward over the WFST. Here we compare CDCCF to other ASR models. As we can see, most are directed models, or say locally normalized ones, including DNHMM, CDCRNT, and AED. From the graphic model representation, it is clear CDCCF is indeed a CF, which is fundamentally different from all history models. A closely related work to our work is single-stage lattice-free MMI. It casts as a discriminative training of an HMM, uses two-state HMM topology and including a silence label. In contrast, CDC-CRF is cast as a CRF, use CDC topology, and there are no silence label used. These features make CDC-CRF have a simpler pipeline and avoid ad hoc tricks. A summary of more comparisons. In addition to the differences just described, CDC-CF has another two good points. We observe the posterior is still dominated by blank in CDC-CF, so that we can speed up decoding by skipping the blanks. And there are no lens normalization nor KMHM in CDC-CF, so the implementation is simplified in CDC-CF. We conduct a series of experiments on three widely used benchmark datasets: the WSJ 80-hour dataset, switchboard 300 hours, and the LibreSpeech 1000-hour dataset. In early version, we use 6-layer BRSTM, and in all the three benchmark datasets, our CDC-CF outperforms CDC significantly. The water error rate reduction at least 10% up to 40%. And the CDC-CF outperform end-to-end change significantly and performs slightly better than the hybrid one. Compared to other contemporary models around the year 2020, CDC-CF also performs very competitively with those models. The results of LibreSpeech are similar. And we can also show CDC-CF achieve better results on AI shell, a Mandarin dataset, and also on children's speech recognition, outperform both Caddy chain model and ASP.NET transformer model. Previous results are based on BRSTM. Recently, we upgraded BRSTM neural net to be conformous. We can also further take experiments with word pieces to show the capability of CRF in the case of not using pronunciation lexicon. Word pieces slightly word pieces systems slightly worse than monophone, as we show here, presumably because in English there is a low degree of graphening to phoneme correspondence, so pronunciation lexicon is beneficial for improving recognition performance. For high degree, for example, German, there is a high degree of graphening and phoneme correspondence. The word pace system perform close to for models. And here we show further results with LM rescoring. We can see that the CF achieve competitive performance when compared to other top conforming systems from the literature on the switchboard dataset. Okay, here we comes the summary of the CF model developed for end-to-end ASR. It inherits the data efficiency of the hybrid approach and the simplicity of the end-to-end approach. CF significantly outperforms regular CTC on a wide range of benchmarks and is on par with other state-of-the-art end-to-end systems over different data sizes and languages. And the CF model also shows great flexibility in other research directions. For example, we have pursued the streaming ASR, the neural architecture search, and the multilingual and cross-lingual ASR in the CTC-CF framework. Okay, next we'll show the successful. Now we have shown the successful application of CF for speech recognition. Next, we'll show how to improve CF in natural language processing. Here, first comes the motivation. Conditional random fields have been shown to be one of the most successful approaches to sequence labeling, and the various linear chain neural CFs, as we introduced before, have been developed. The load potential modeling is improved by using neural networks, but the linear chain structure is still kept, for example, by using a background table as a edge potential. In this way, the linear chain neural CFs capture only first-order interactions and neglect higher-order dependencies between labels, which can be potentially useful in real-world sequence labeling applications. It can be seen that a fixed nth order model can be equivalently cast as a first-order model. So preferably, we would like to develop a non-Markov model. So a natural question is, how can we improve CFs to capture long-range dependencies in label sequence, preferably by a non-Markov model? Extending CFs to model higher order interactions beyond of the pairwise relationship between labels is an important issue for sequence labeling. And there have been some previous studies, such as the infinite order CFs, which based on the hierarchical Putman-Yor process, which is a kind of Bayesian non-parametric model. And semi-Markov CFs, latent dynamic CFFs have been developed, but these previous CFs extensions do not use neural networks. More recently, the attention-based encoder-decoder AED and RNT have been developed, which exploit non-Markovian dependencies between labels, but both are locally normalized models, and thus suffer from the label bias and the exposure bias problems. The work of deep extends AED by removing the final softmax in the RN decoder to learn global sequence scores, but it casts as a non-probabilistic variant of the sequence-to-sequence model. In the work of Yi, one of our work published in ICASSP2022, we propose a neural CF transducer, which basically is a marriage of RNNT and CF to improve high-order interaction modeling. So Next, we'll first introduce the INT and then introduce the CF transducer. The INT transducer, INT is the full name is INT transducer. It is originally developed for general purpose sequence-to-sequence learning, which do not assume the input and output sequences of the same lengths of equal length. For example, in speech recognition, in the following, since we introduce transducers for natural language labeling, which is a line setting, so we present the transducer in a simple form, that is for the aligned setting, one label for one observation in each position. And a similar idea can be used to revise general INT. Okay, the motivation of INT is to extend CTC by considering output dependencies. There is a transcription network F, which scans observation sequence X and output hidden states F, each of k-dimensional at each position. And there is a prediction network G, which scans the label sequence Y0 to Yn, and Y0 is said to be the special token, the beginning of the sentence token, and scan the label sequence and output hidden state G, which is also each of k-dimensional. In addition to the transcription net and the prediction net, INT introduce the joint net called JN to define the conditional output distribution. The input of the joint net is a hidden state from the transcription net and the prediction net, the F and the G. And the output is softmax over K labels. So based on Fi and Gi, we can use a softmax to produce a distribution over K labels, which is a conditional output distribution, which further defines the conditional distribution of Y given X. As we introduce the INT, it can be easily seen that it is still a directed sequential model, or say autoregressive model. So INT potentially suffers from exposure bias and label bias. Recent work is in this paper, which uses scheduled sampling to alleviate somehow. Now we can introduce the new model, the neural CF transducer, which is a marriage of INT and the neural CF. Yep, INT is locally normalized. The local conditional is a softmax. Is a softmax using hidden states from the transcript net and prediction net respectively. And the linear chain CF is global normalized. But the edge potential only captures first-order dependencies between labels. So we can develop neural CF transducer, which combines the advantages of INT and CF. It is global normalized, as shown here. This model definition still applies to the CF transducer. but it can capture long-range dependencies between labels. The magic is a new definition of the edge potential. Here, the edge potential calculated as the sum of F and G, so that it actually involves the history labels in definition, because the G is calculated based on history labels. Okay, the training loss. Okay, let's discuss the training and decoding with CF transducer. The training loss is usually the elective log likelihood of input sequence X and the oracle label sequence Y star. And we can use the multicolor method, but the difficulty is that we need to sample from the model, which is intractable. There is another method called bin search with early updates. The idea is to define the objective with approximation to the normalizing constant. The constant contains all paths in the beam together with the oracle path prefix. It is empirical find that the method of bin search with early updates marginally outperforms the Monte Carlo methods for training CF transducer, because the sampling for CF transducer is more difficult to implement, and we can use bin search for decoding. Here we show the experiments on the number of natural language labeling tasks, including the part of speech, chunking, English name entity recognition, and Dutch name entity recognition. Experiments show CF transducers achieve consistent improvements over linear chain CFs and ion transducers across this sequence labeling task and obtain state-of-the-art results. You can find more details in the reproducible code in this link. Okay, so that's the end for Chapter 3. In Chapter 3, we mainly introduce energy-based models for modeling conditional distributions. So with applications mainly in these cumulative tasks such as speech recognition and natural language labeling.